everyone, I'm Yunpang. So now just let's move the focus from United States to Germany. I have to say that it is an ongoing work. So today we would like to share some initial results and findings in our work. So firstly, motivation. Just like we have heard yesterday and today, there are already a lot of trajectory data. They are available and they can provide deeper insights in not only in traffic dynamics, but also in the interactions between road users. But at the same time, such data also create some different kind of challenges if we want to put this data into the microscopic simulation. So last year, one date of trajectory data from our research intersection in Braunschweig was published. Our focus here is try to use this data set and to see how trajectory data can be used to build a traffic simulation in SUMO. And also we want to see how well SUMO can reflect the traffic conditions with this data set. So now I would like to provide you some basic information about this research intersection. And here, this intersection is actually well equipped with different kinds of videos, sensors, and these systems, they continually collect real-time data, so for 24 hours. And as shown in these three images, you can see that the blue sensors, they focus in the inside area of the intersection, while the green ones monitor the outside area of the intersection. So this setup just try to make sure that we have the full coverage for this intersection, and that we also want to minimize possible occlusion, and also want to capture the key objects in the central area. And additionally, we have also 4 rate sensors on the pedestrian crossings just to enhance the detection quality. And at the end, we have another additional 2 purple sensors. They assist in analyzing the interaction of pedestrians on sidewalks. So that's the background about our intersection. And regarding the data sensing, the data processing, the data set we used is also available in Tenodo. So if you are interested, you can just download this data set and try to use it with SUMO together. And just like I said, the trajectory data were collected by video cameras. So these objects in the video were identified through an object recognition system. And then there are totally 6 different object classes, from car, van, trucks, motorbike, bicycle to pedestrian. And that is the nice thing, that we also have the trajectories from bicycles and pedestrians, because they do actually interact with vehicles at the intersections. So this data can make the simulation more correctly. That's what we hope. And speeds and the accelerations were actually derived from object positions, and that were smoothed by Kalman filters. Otherwise, the data will be have too much noises. And beyond the trajectory data, we also have traffic light, weather, and air quality information in this data set. And all these data were collected at different sample rates. Trajectory data is every 0.05 seconds, and traffic light and air quality data is every second. And weather data will be collected every 10, 30, or 60 seconds. So just like the other trajectory data, even we have a very good coverage. We have different kind of detectors, but there is still a need to do some data cleaning and corrections. And due to the process glitches, some trajectories are fragmented. So this is actually very crucial for reproducing data in SUMO. Some of them can be repaired during post-processing, but others remain incomplete. So if it happens, then this can result in uncertainties in the vehicle origin, destination, and also departure speed and position, even the shorter travel distance. So to this point, we have removed the objects where the distance between their start and end points less than 6 meters. So it's like, I hope you can see that it's a small example here. So that means the trajectory is just running in a circle. So for such case, we just remove the trajectories. And moreover, we also found out that some object classifications are not really certain. And here we provide an example here. Originally, these trajectories were classified as pedestrians. So we just plotting them on a satellite image, and then it becomes evident that these trajectories are not really pedestrians trajectory, but bicycle trajectories, because they are actually on the bike paths, and then they all traveling with a higher speed. So regarding this issue, we also made several corrections and reclassifications, not only for pedestrian, but also for motorbikes and bicycles, according to their traveling speed. And we also observed that there are some very slow working speed, less than 1 meter per second. So we just adjust them to fall into a normal range, so around 1.5 meter per second. And lastly, as you can see here, the bicycle paths are available in all directions. So we just removed the trajectories for bicycles with illegal direct U-turns. And such situation happens also not so often, very, very, very rare. So that's what we have done for the data correction and cleaning. And for the simulation network, we use the OpenDrive map, which is generated from the VVM research project. So as you can see, the accuracy of the OpenDrive is already quite high. And that's the reason we would like to use this to ensure that the road and intersection geometry closely reflect reality. So here we also made several adaptations with our SUMO network. So as you can see here, including we adjusting the stop lines, we change the lane widths, we adding the roadside parking areas and also dividers. And as you can see here, that's the final network, and it fits very well with the respective map, which is shown in blue. So that is our playground. And now we are sure that at least the geometry is correct, and it is very important, especially for the trajectory matching on the network, so that we are sure that the trajectory should be matched on the correct position in the network. And additionally, we also changed the allowed traveling speed for each edge, and also the turning curve within the intersection, as well as the allowed turning movement in each vehicle lane. And the next step is generating traffic demand. Our approach is that we would like to generate a trip-based travel demand, and this demand can properly reflect the real traffic condition, like everyone. But therefore, we also use the trips derived from incomplete trajectories. We don't want to throw them out. Otherwise, maybe the traffic demand will be underestimated. So we still keep them to make our simulation quite reliable, realistic, But at the same time, we only use the complete trajectories to do the calibration and the comparison with the real data. So to the trajectory matching, it is done in 2 steps. In the first step, it relies on the predefined polygons start and end. As you can see here, the red ones are for vehicles, and then green ones are for bicycles and pedestrians. And for those trajectories that cannot be matched in the first step, a second matching process will be applied according to the marking, the turning markings in each vehicle lanes. So we do that step by step. At the end, the daily trips consist of 27,000 vehicles, 1,600 bicycles, and 240 pedestrians. That is our basic input data. So, but before running the simulation, as you all know, we still need some data, some information about the traffic signal. So we are lucky, we have the traffic light data directly from the video cameras and also from the sensor systems. So we just try to parse and match the traffic IDs and the traffic light states, and then to create additional file for traffic signal control in SUMO. And here I have to emphasize is that this intersection figures adaptive traffic control. So that means the green time duration varies when the traffic flows are different. So that's the reason we need to parse this information and then to fit this to the simulation. So we run the simulation with the traffic demand between 7 and 8 o'clock. So there are around 1,200 road users, 90% are motorized vehicles, and most of them are passenger cars. On the right-hand side here, you can see we try to compare the simulated and measured trajectories of a vehicle making a left turn from north to east. And because these trajectories are incomplete, so we have to adjust its starting point. And that's the reason why the trajectory for the simulated vehicle is longer than the real one. And we can see that the turning curves of these two vehicles align very well together within the intersection. And after the turn, the simulated vehicles update a different lane. So then you see the deviation from these two lines. And regarding the travel speed, in general, the simulated travel speeds are somewhat higher than the measured ones. So that means that we have to do the calibration for the next step. And you can also see here, there are also some situations here that the simulated and the measured speed, they diverge in opposite directions. So the reasons we think it could be firstly different driving decisions during the yellow phase time. Some drivers decide to stop, some drivers decide to go for it, just passing the yellow phases. And the other reason could be the inconsistent synchronization of the traffic signal control, and that we have to further investigate this point. And it could also be due to the uncertain quality of the input data regarding departure position and the departure time. So once the departure time is perhaps only 2 seconds later, then this vehicle has to stop there and wait for the next green time. And then it could result in this situation. The last reason we think is because of the unexpected departure delay in the simulation. We have checked some user cases, and we found out that some of them are due to the situation check, safety check from SUMO itself. SUMO will check before SUMO let a vehicle into the network. So due to that, we also take out the junction check. So that means it could happen that there will be junction collision if we don't consider this check. But right now, for this case study, we have not get any collision result. So in addition, we also see that the difference between the vehicle classes, I just said that we have like 4 different classes, car, vans, trucks, and motorbikes, but we don't see any significant speed difference. So this raises actually a question of distinguish them for calibration is necessary, or we can just put them together and then try to calibrate one parameter for this 4 vehicle class. That's what we will do later on as well. And last, we also check the speed difference per OD relation. And the average speed difference per OD relation is about 1.5 to 4.5 meter per second. And we found out that the smallest speed difference occurs in the direction from north to east. That's the left turn traffic. It is kindly due to, firstly, the less left turn traffic, and secondly, because of the adaptive traffic control for left turn movements. So they don't have to wait for a long time. They can always get a priority to get a green and to cross the intersection. And in contrast, we see that the right turn traffic has greater speed differences and across all 4 directions. So the possible reason, we think it could be that there is less interaction between vehicles, pedestrian, and bikes in the simulation. So that means perhaps we need to recheck if the pedestrian classification is okay, or maybe we're missing something. We have to put more pedestrian, or we have to look at the departure time again. And it is also possible that we have not considered the roadside parking effect. There are actually roadside parkings in 4 directions. So maybe that's the reason the right turn traffic cannot drive so fast as what they can in the simulation. So maybe we need to consider this effect as well. So to remarks and next steps, I think up to now, as I say, it's ongoing work. Up to now, our work shows that SUMO can actually microscopically reproduce traffic situation with the trajectory data and traffic line data, although future calibration work is still needed. So we will do that. And the next is further data examination and correction are required, especially for object classification and also for vehicles traveling with much higher speed, because we also experienced that some vehicles, they cannot enter the network with the given departure speeds. But the departure speeds are what we have derived from the raw data. So we have to look at this as well. And the necessity of vehicle classification for calibration, just like I mentioned, we also need to look at it if it's necessary, or we can drop it. And the 4th point is that, as I mentioned, this intersection figures adaptive traffic control. So that means it makes the scenario analysis very difficult, because the green time duration changes when the traffic flow changes. So if we don't have the control mechanism, then we can not try different scenarios, and that is the case. We don't have the control mechanism. So our idea is to try to check the applicability of SUMO's actuated traffic control method, and to see if we can just use this method in SUMO and then to get a similar result or representative result. And then the last one is the overall data processing and simulation procedure. We would like to further improve it, and we hope that this whole process will be later on published as open source, and then people can use it, easily set up the simulation and even transfer to a different intersection. So that's my presentation. Thank you very much for listening.